Consider the following curve. F of x equals x cubed minus 12x. Now, let's say that we want to find these two critical points. Okay? Now, what's special about these 2 points? Okay. This point up here, it's not the maximum of the curve. It's not the highest point. The curve goes all the way up to positive infinity, but it is certainly a local maximum. It is the maximum in this area, meaning all points in the general area of this one are less than that. Okay, that's a local maximum. Similarly, this other point down here is a local minimum. All the points in its vicinity are actually greater than that. Okay, so how do we actually find these critical points? We can use calculus to do this. And you can think about the tangent line, right? The derivative of this curve, okay, we can say what it is. It's f prime of x equals 3x squared minus 12. And that gives us the tangent line at every point on the curve, including these two. But these 2 points are actually special, because if you look at their tangent lines, you can see that they are in fact horizontal. And what's so special about horizontal tangent lines? Their slope is 0. So for these 2 points, we get m equals 0. Okay? Now, there are many applications for these types of points. Okay? If someone asks you to graph f of x equals x cubed minus 12x, you certainly want to know where those points are. It also gives you, generally speaking, the minimum and the maximum of curves, ignoring for a moment the endpoints. Okay? What do I say the endpoints? What do the endpoints have to do with it? They have a lot to do with it, because if we restrict this to just a certain interval, okay, let's say we're looking at just the interval from here to maybe here, okay, what does that have to do with it? Well, in this case, the minimum of this curve, and what we could do is even shade it in pink. So basically it's the same curve, but we're just looking at now, you know, this part of it. Sorry, not easy to trace over on this board. If we look just at the pink curve now, and we want to know what's the minimum and maximum of the pink curve, well, the maximum you can see is this endpoint here, and the minimum is here. Okay? And what we're going to do now is put all of this together. And let's consider the following. Okay, so we're going to transform this into a problem. The problem will be given f of x equals x cubed minus 12x, and we're going to give an interval. Okay, so we're going to give an interval, and let's say that x is between what? Okay, what is x going to be in between? How about -3 and 5? And our goal is to find the minimum and maximum of this curve with this interval. Okay? Now, we need to consider each of the following points. We need to consider the critical points, which calculus will give us, and the endpoints, which are provided right here. And then we have to, in effect, compare them. So let's first focus on the calculus piece. How do we get these critical points? As mentioned, you can take the derivative and set it equal to 0 because m is 0. So if we set this equal to 0, we can then solve this. We get 3x squared equals 12, or x squared equals 4. So x equals plus or minus 2. Okay? Now we have all of the critical points. So all we have to do to compare them is to, in effect, plug them in. Okay? Now when you plug in the points, what you're doing is you're plugging them into the original curve. Okay? You're not plugging them into, say, the derivative. Okay, so let's go ahead and do that. Let's start our points here. And so let's say what is And let's just start at the top. What is f of 5? Okay, f of 5, right, that's one of our critical points. We plug in to the original, well, 5 cubed is 125 minus 60 is 65. Okay, that should be really way up there. Great, now let's move down. We've got f of 2. Right? Yeah, f of 2. So what's f of 2 equal? Well, let's plug it in. We've got 8 minus 24. So that's negative 16. Now by symmetry, well, let's just check it. What's f of 2? Let's find out. So we got f of 2 in this. Now let's make it, put it over here. F of 2 equals, okay, 2 cubed is 8. I'm sorry, I just did that. We need negative 2. Okay, so f of negative 2 is negative 8 plus 24 is the positive 16. And finally, we need to get f of negative 3. And so for f of negative 3, let's see, we get negative 27 plus 36. That gives us a positive 9. Okay, so we can see from these computations by plugging into the original that one of our endpoints, f5 equals 65, is in fact the maximum of the curve, and the minimum, the smallest value, f of 2, is negative 16. So that's the maximum and minimum of x cubed minus 12x, given the interval that x is between negative 3 and 5. If we don't have any interval there, there is no minimum and maximum, right? Why is that? Because it goes off to positive and negative infinity, okay? But the critical points are still plus 2 and minus 2, okay? Let's do another one. Get some additional practice in here. Now for this next one, let's consider the following. Okay, let's do another example here. F of x equals, and we've got x cubed minus 3x squared. And then we've got minus 9x plus 5. And the goal here is going to be to find the critical points and determine if it's a minimum or a maximum, okay? So, how do we do that? As shown here, we take the derivative and set it equal to 0. Okay, so we do f prime of x equals 3x squared minus 6x minus 9, set it equal to 0. Now we can divide this by 3, and then what do we get? We get x squared minus 2x minus 3 equals 0. And this will in fact factor, it looks like, so we've got x minus 3, x plus 1 equals 0, and so we solve this by x equals 3 or negative 1. Okay, now we've got 2 critical points. Okay, the next step is to determine if it's a local minimum or a maximum, and there are actually different ways of doing this. Now, it doesn't actually work just to plug them in. And the reason why is because you can imagine, right, if you get that there's a point here, okay, well, without any other information, you don't know if the curve goes above it or below it. Okay, now you can use other information to figure that out. I'm going to show you a couple of standard ways of doing this. Okay, they're both very useful. Okay, the first thing that we're going to do is we're going to look at the interval that includes these points. So we've got the critical points negative 1 and positive 3. And what we're going to do is we're going to look at what happens to the derivative, and the derivative is here, okay, f prime of x, and we're just going to plug in a value and see what we get. Okay, so let's just look above 3. Now above 3, you get 4, okay? So if you plug in 4, everything's positive, right? Okay, we're looking right here. We're looking at x minus 3 times x plus 1. Both of those are positive. Positive times positive is positive. So the derivative is positive greater than 3. Now, if we plug in 0, we get a negative here and a positive. Negative times a positive is a negative. And so the derivative is negative between negative 1 and 3. Okay, and finally negative 1. What happens, say, at negative 2? Okay, at negative 2, they're both going to be negative. Negative times a negative is a positive. Okay, how does this help us? Okay, because if you look at what the slopes are doing, okay, imagine the tangent lines. Here the tangent lines are positive, and after that they're negative. When the tangent lines go from positive to negative, it is a maximum. They go from positive to negative, this is a max. Similarly, if the tangent lines go from negative to positive, it is a minimum. So this is a minimum. Okay, this is like an interval notation thing. It's a very useful technique. And what we're doing simply is we are analyzing whether the slope is positive or negative. Okay? There's another way to do it. And I do think both ways are actually useful, and both are somewhat standard in calculus. Let me show you the other way. The other way involves a second derivative. And it's useful if it's not too difficult to take a second derivative, which in this case I would say it is not. Okay, so we've got f prime here. What's f double prime? Let's find out. F double prime of x is 6x minus 6. Okay, now we haven't talked about f double prime, we just got it. So what's the deal with f double prime? Well, it kind of measures what we just did. It measures something called concavity, okay? So concavity works as follows, okay? This right here is concave up, okay? Concave up. And what's happening here, if you imagine the slopes are negative, slopes are becoming 0, slopes are becoming positive, the slopes are increasing, okay? So you could say slopes are going up. And then concave down is the following, okay? This is concave down. In this case, you start with a steep slope, right? You're imagining tangent lines. But it's getting smaller, smaller, 0 gets negative and negative, so your slopes are going down. But it should be clear from this that if you have a concave up, this is going to be a minimum, right? That is a minimum point here. And when you have concave down, your point is going to be a maximum, okay? So you can use the second derivative, plug in the points to determine if it is going to be a minimum or a maximum. Okay, let's try that. So if we plug in f double prime of -1, what do we get? We get -6 minus 6, -12. Okay, so if we're getting a negative on a second derivative, that is concave down, and that means it's a max. Okay? Similarly, what if we plug in f double prime of 3? What does this equal? Okay, well it's you know, the number doesn't matter. It's positive. Okay? It's, you know, it's 6 times 3 minus 6 is greater than 0. But whatever, it's 18 minus 6 is 12. Okay, 12. It's positive. What does positive mean for concavity? It means it's a minimum. Okay, so this gives us a minimum. Okay, so that's two different ways to determine if the critical points are minima or maximum. Now, I want to close with an interesting application, and this is with quadratics. Okay, so it's another example here. Get a better pen, marker. Okay, Quadratics, we're going to generalize, and we can generalize them using the following. Ax squared plus bx plus c. Right, this is a general quadratic. And, you know, if you just look at it, I mean, it could be up, it could be down, we don't know. But all quadratics have either a minimum or a maximum, okay? Calculus can deliver that to us. Now, you may know the formula to get that point, which is the vertex of the parabola. But we're going to use calculus to actually get it. Okay, so how would we do that? Okay, there's our equation, let's use it. So we've got f of x equals ax squared plus bx plus c. Okay, and now we're going to take the derivative. So you get f prime of x equals 2ax. Remember, a and b are just numbers. Plus b, right? Number times x, derivative is just that number. Now we've got to set it equal to 0. Right? That's what we're doing here. We are taking derivatives, we're setting it equal to 0. It gives us the critical points, and in parabolas, it always gives you the minimum or the maximum. Okay? So this will work for any parabola. We just solve for x. X equals, and you get the famous formula, negative b over 2a. So you can derive that formula using calculus. And I will also say this, unlike with the cubics, they're going off to positive and negative infinity, in the parabolas, in the quadratics, you always have a minimum or a maximum. So what we're doing here is we are really finding minima and maxima, okay? But this is incredibly significant because the minimum and the maximum could be for certain real things, like how do you maximize profits? How do you minimize surface area if you're building the size of a box? Okay? These types of questions. Minima and maxima fall under optimization problems in calculus. And that's what we'll look at next.